All right, we're going to continue our discussion on reaction mechanisms. All right, so what we'll see in organic chemistry is a reaction that is going to be called the SN2 reaction. All right, so we got capital S and then an N, and it's kind of lower justified, and then the number 2. All right, and what this translates to is something called substitution, nucleophilic, bimolecular. All right, so the S is substitution, the N is nucleophilic, and the 2 stands for bimolecular. All right, so in the SN2 reaction, what we have is something called a nucleophile. All right, and we're going to give it the symbol Nu. All right, and it attacks something called an electrophile, E. All right, and E has this leaving group X, and what ends up happening in this reaction is we substitute. Nu gets X and E gets kicked out. All right, so that is essentially the substitution process. Right, we're substituting out E for Nu. All right, and what I want to just show you is why this thing's called bimolecular. All right, because in this case the reaction mechanism is the single one step. All right, so not only is this the elementary, it's also the overall. So this is the elementary and the overall. So what's cool about that is that allows us to write the rate expression quite easily, like so. All right, because that's like our A plus B in the previous video. All right, so it's bimolecular because the rate of the reaction depends upon both the nucleophile and the electrophile. All right, so there's another one that you'll also study called the SN1. All right, and this is substitution, nucleophilic, unimolecular. All right, so the reactions are identical. All right, the overall. Okay, so let's go back. Right, exactly the same. However, the mechanism is not the same. All right, so what ends up happening with this reaction, all right, is that we have the not the nucleophile. The electrophile undergoes a dissociation process in the first step. So this is elementary step 1. All right. Then X will react with Nu to form NuX. This is elementary step 2. All right. So if we add those up, we see that we get EX, and the X's cancel, right? Plus Nu gives me NuX plus E. Okay, so it looks identical. So it's unimolecular. So why do they call it unimolecular? Well, through the study of the kinetics, which you'll spend more time in organic, it turns out that this is what we call the slow step. And the slow step determines the overall rate of reaction. Okay? So when you have a multi-step reaction and the first step is slow, that's what we call the rate limiting step. So the slow step is something that we call the rate limiting or rate determining step. All right. Now, why is that? Okay, so if you think about an everyday process, okay, like let's say if you want to pull out of the street or onto the street, and we've got a street here, and this is where you are. And let's say you want to get going in that direction. So you have to cross this 2-lane highway where the traffic patterns are like so, okay? And you want to make your turn here, all right? So just think about this. If you're driving, all right, and the lane up here is totally clear. There's nobody up there in that lane, right? But this lane is totally clogged. Are you going to be able to get into your lane? And the answer is no, because you got to sit here and wait and wait and wait and wait until this lane clears, all right? So that's kind of the idea behind rate limiting or rate determining steps. You can do 50 different processes, right? But if one takes 10 hours and the other all take 1 second, right? Which one is really determining the rate of that process? The one that takes those many, many hours, all right? So when something slows you down, all right, that's what you're going to be waiting on, and that's what we call the rate limiting or rate determining step. So the rate determining step literally determines the rate of reaction. So if we go back to our SN1, our slow step is elementary step 1. And since we have an elementary step, we can write the rate law. Rate equals K EX. And since it is only dependent upon EX, the slow step, we call this unimolecular. All right? I apologize, it doesn't do as well down at the bottom. Okay, so it's unimolecular. So the SN1 reaction will be unimolecular, and the SN2 reaction is bimolecular. All right, so that's where we see that. Okay, the next topic I want to get into is something called catalysis. All right. So what do catalysts do? One of my favorite definitions of a catalyst is that they provide an alternative mechanism which either decreases the activation energy barrier of the rate determining step, or destabilizes. We'll just leave it at that. That's good enough. All right. So what ends up happening here is it will change how the reaction works, thus lowering the activation energy barrier in this slow step. So if we look at, for a classic reaction, the depletion of ozone, all right? So the depletion of ozone in the upper atmosphere happens naturally when ozone encounters an oxygen radical, all right? So O, oxygen radical, and that's going to give us 2 moles of oxygen gas, all right? So that happens naturally, and it's quite slow, all right, which is a good thing. We want that ozone layer up there. However, radical chlorine, right, that can come from things like CFCs can really speed this reaction up, breaking it up into 2 steps. All right, so these are 2 separate reactions. Okay, the one on the top is the natural, slow one, and the one on the bottom is a catalyzed version. Okay, what is the catalyst? How do you identify what a catalyst is? Let's look at what happens. Chlorine, one single chlorine radical, is consumed in the first step, and then it's produced as a product in the second step. This is bad news for this particular reaction, because if you release chlorine at the end of the reaction, guess what it can do? it can go and catalyze another reaction. So in theory, one single chlorine radical could destroy the entire ozone layer, right? Fortunately, something else happens to that chlorine up there. This isn't its only fate, okay? But in theory, yes, one single chlorine radical could destroy the entire ozone layer. That's what makes catalysis pretty neat and can be quite scary, all right? Because you just need a little bit of this to kickstart the reaction, right? Because what ends up happening is you speed up the reaction by lowering the activation energy barrier. And then what's really neat is you kick it out at the end, all right? So when you have a reactant that is consumed in the first step and then produced in some final step, then that's what you consider a catalyst too. All right, so you'll see in organic chemistry that reactions are catalytic in water quite often. So if you add a little bit of water to the reaction, it'll be consumed at the beginning of that reaction. It'll speed the reaction up, and at the end, it kicks out that water. Okay, so there's two types of catalysts, all right, that are out there. There's what we call heterogeneous. And these are not part of the reaction phase, all right? So for example, you can have something called catalytic hydrogenation, where we take H2 gas, all right? And if we put in platinum catalyst, right, which is a solid, we can catalyze the reaction to give us H plus H, okay? So what we'd say here is that we're in the gas phase for hydrogen and we're in the solid phase for platinum. These are in two different phases, so it's heterogeneous, all right? The other is what we call a homogeneous catalyst, where they would be in the same solution. All right, so for an example, you could have, hydrolysis, where we add water to a reaction. So if we take water plus ethene, and let's say this is a liquid and this is a liquid, we could have this reaction. All right. Now it turns out that this reaction would be extremely slow, but what we can do is we can add acid, all right, in the form of H3O plus or hydronium ion. And if that's aqueous, that's going to catalyze this reaction. So if we're in the liquid aqueous phase, this is a homogeneous catalyst, all right? So the reaction becomes much, much faster when we add hydronium. Now, how would you have known that? Don't worry about that. That's not what's important. What's important is you can tell the difference between a heterogeneous catalyst when it's in a different phase, and then we have a homogeneous catalyst when they're all in the same phase, all right? So if we go back to that ozone depletion or, degradation of ozone, all right, the naturally occurring reaction looked like this, all right? It happened in a single step. So let's just make a pretend curve here. I have no idea whether it's exothermic or endothermic. It doesn't matter, right? That's what that curve would look like. However, if we were to look at the catalyzed reaction, where we take O3 plus Cl going to ClO plus O2, and then we have the ClO plus O going to Cl plus O2, all right? That happens in two steps, all right? And the rate determining step for the red reaction is kind of trivial, right? Because there's only one step, so itself is the rate limiting step. So what has to happen in the second reaction is it's going to change the mechanism to make it look something like that, all right? How do I know it happens faster? Well, look at those activation energy barriers for the blue, all right? It happens in two steps, right? Because here's step one for elementary reaction one, and there's step two for elementary reaction 2. All right. So 2 steps, going to give me 2 humps, if you will, and 1 step gives me 1 hump. All right. So there's some things we need to talk about in here. All right. They're called the transition states and something called intermediates. All right, so intermediates, they show up in multi-step reactions. All right, these are something that are going to be a product in an elementary reaction. That is consumed in a subsequent step. All right. So, which reaction has an intermediate, okay, and the transition states, all that good stuff. So why don't we just go ahead and break these curves up into 2 different ones. Let's look at the O3 plus O going to 2O2. There's the curve. All right. So we can answer a few questions. How many steps does this reaction have? And the answer is 1. Okay, 1 step. How many transition states does this guy have? The answer is 1. Okay. How many intermediates? The answer is 0. Okay. In order to have intermediates, you're going to need more than 1 step. All right. So there are no intermediates in this reaction, just 1 step and 1 transition state. Okay. And that transition state, of course, is there. These are our reactants, A and B, and this is our product C over here. Okay. Let's look at the catalyzed reaction, where we took O3 plus chlorine gives me ClO plus O2. Then we have ClO plus O goes to Cl plus O2. So it's curve. Looks like that. All right. And how do I know this? All right. Well, let's look. How many steps does this guy have? The answer is 2. All right. What order of questions did I do? Okay. So transition states. The number of steps will always equal the number of transition states. All right. So we go through step 1, have a transition state. This is TS1. And this would be over here, TS2. So you see the pattern here? Transition states are what? They're going to be the peaks on these curves, all right? Or what we call the local or global maxima, all right? Next question, what did I ask last time? Intermediates. Where are the intermediates? They're the resting points, all right, on the curve. So what I'm going to do is give it this red color, I. Right, that's the intermediate, okay? So if we had to label everybody on here, this guy would be reactant A. So we have A here. This guy's the catalyst. Okay. And notice the catalyst appears here. All right. Catalyst consumed and then reproduced at the end. All right. We have the intermediate, right? The intermediate is what is produced. Oh, man. I got to quit drawing at the top. That's the intermediate, as is this. Okay? What is O2? Well, that's a product. We'll call P. O, that is a reactant. We'll call B. And this guy is also a product. We'll call P. All right? So we have A and B here, and then P over there. All right? So A, B, those are our products. A, B, those are our reactants. Then we have P as our product. I is our intermediate. And then we have two transition states. Notice the catalyst does not appear on the reaction coordinate diagram. So back to my question, how many intermediates do we have? 1. All right? So look at this. The number of steps equals the number of transition states. Nice. The number of steps minus 1 will also equal the intermediates. All right? So let's say you have a reaction with 62 steps. No, I'm just kidding. I'm not going to draw that. Let's do that. Okay? What the heck is that? Whatever. How many peaks does it have? 1, 2, 3, 4. That's a transition state. That's a transition state. That's a transition state. And that's a transition state. So the number of transition states equals 4. That also means we have a 4-step reaction. Okay? So if we have steps equals 4, transition states equal 4, intermediate should be equal to 3. Let's see if we can figure that out. They're the valleys. Cool. 3 of them. All right? And what's this? The very beginning is the reactants, and the very end is the products. Okay? Is it exothermic or endothermic? How do you measure that? The difference between the reactant and the product. Okay, in this case, it is delta H is negative, so that is exothermic. What's the rate determining step? All right, that's going to be the one that has the highest activation energy barrier, and admittedly, that's going to be a little hard on this goofy diagram, but I can clean it up on a better one. Reactant, product, TS1, TS2, and I. So this is a 2-step reaction. So how do you measure the activation energy barriers? There is one, and here's the other one. Okay, so that's EA1 and EA2. Okay, so the intermediate going to transition state 2, that's the activation energy barrier for step 2. Looks like EA1 is much larger to me, so this is going to be the rate limiting step. Is R going to I. All right, that is the slow step. All right. Last thing I want to talk about are catalysts and biological reactions. All right, so some of the most effective catalysts in all of nature are the ones nature actually designs. All right, so we use catalysts like platinum and so forth, and things like catalytic converters. Right, those are metals in there that help break down some of the nasty gases that are coming out of your engine. All right. But nature designs their own, and one class of these catalysts are called the enzymes. All right. So enzymes are biomacromolecules, or globular proteins, if you will. That catalyze biochemical reactions. All right. So one example of this is what's called the lock and key model. All right. So we have something called a substrate. And this is essentially the natural substance that the enzyme operates on. All right, so if we had something like acetylcholine, for example, all right, that is a molecule in your body, okay, and this would be a reactant of some sort. Or serotonin, that's another substrate that's in your body that gets operated on by enzymes, all right? So we can typically draw these little cartoons of them. Okay, it has this shape, all right? And it's all about shape, huge importance, okay? Because it's like lock and key. Enzymes are kind of like the lock, and only certain keys, which are the substrates, will fit into them, all right? Now, we can have the enzyme, which is the catalyst. All right. And let's just draw this little Pac-Man looking dude. So you have this guy called S here, and this guy called E. And we're going to make something called the ES, or enzyme substrate complex. So this is the enzyme substrate complex. And then what ends up happening now is your enzyme releases after it does its job, breaking up the substrate into two different products. So this is what you call E and P. All right. So it's catalyzed this reaction. Okay. So in most enzyme kinetics, we have E plus S, which is our fast step. We get the enzyme substrate complex, and we have a slow step here to give us E plus P. All right. And if you take physical chemistry or biochemistry, you'll study these enzyme kinetics in a lot more depth than here, but this cartoon just kind of shows you how they work, all right? And they are extremely fast and extremely selective, all right? So one cool class and an easy one to look up if you have some free time is these acetylcholine esterase inhibitors. All right. They're pretty cool. All right. They are acetylcholinesterase is the enzyme. All right. And there's human versions of them, okay, that have been targeted as anti-Alzheimer's. Right, and there are mosquito versions of them that are quite a bit different, that are targeted as anti-mosquito. So when I was a graduate student, I worked in a laboratory that studied acetylcholinesterase inhibitors, and some of us were working against mosquitoes, and others of us were working against Alzheimer's disease. Quite a bit different I guess you'd say endeavors, but they all were after these enzymes. So it's funny how some of this stuff works out. But anyway, take a look. Enzyme inhibitors, really cool stuff, and really getting into pharmaceuticals and pesticides and all kind of neat things. So, all right, that will end our discussion of kinetics. All right, we will pick up tomorrow getting into equilibrium. All right, thank you very much.